Hello, everyone. My name is Afolabi. My team members are Rakuya and Rotimi. Our presentation is titled Data Center Networks, Features and State of Art. Our references for this presentation are IEEE publications, which include Rethinking the Data Center Networking, Architecture, Network Protocols, and Resource Sharing, a survey on data center networking, infrastructure and operations, a design for resilient data center networks, IDaaS, Inter-Data Center Networks as a Service. If I ask the class what a data center is, we all will probably have several descriptions of a concept of a data center. In its simplest form, it is a facility that houses compute, storage, networking resources, which power applications and services that we consume either locally or on the internet. Over the years, there has been an increase in the demand for internet applications and services across the world. This demand has been around cloud services such as streaming services, email services, online gaming, etc. Data center network provides that connectivity required for intercommunication between compute and storage resources. This networking has grown from its traditional form of local area network, which we all know as LAN, and wide area networks known as WAN, to a large-scale network of interconnected data centers across the world. So then, what are the basic components of a data center? The basic components of a data center includes compute, storage, networking, and power. The compute comprises of the various machines, servers that provide memory and CPU resources for the various services and applications that we consume. The storage on its own provides that area for data that is processed by applications and services to be stored. Networking provides that interconnectivity between these services. So networking provides that platform for services and applications to communicate with one another. The power component of it is what provides the power that each of these other components require to run. One thing that you'll find that is not included here is, which is also very important, is cooling. Cooling of the data center is of utmost importance, and that is required to keep all devices in good shape and form. Now, challenges of a data center. First is scalability. This just basically answers the question of how easily resources can scale up or down in response to the demand from applications and services. Second one here is variety of applications hosted. In the traditional data center, applications were simply limited to a few numbers which had very limited requirements in order to intercommunicate. But we have found in modern data center that there are various applications that have different levels of importance and have strict requirements for communication. High energy usage. You'd find out that as you add more resources into the data center, as you add more devices, as you seek more expansion, the devices start to consume more. There's more power consumption as more devices are added into data center. Security risk. The attack surface increases significantly as more services and more applications communicate with each other, and security has to be at the foundation of the data center in itself. So network security is one of the challenges that you face as you look into standing up that data center that is resilient and has security as the foundation. One other challenge is poor application deployability, and finally, low management flexibility.
Hi everyone, this is Rukhaya. I'll be continuing from here. DCN architecture is the most important determinant of network performance as it plays a significant role in providing agility and dynamic reconfigurability of the infrastructure for changing application demands. DCN topologies can be roughly classified into four categories. One is the tree-based topology, example fat tree VLDO. Second is the recursively defined topology, example D cell, B cube, etc. Third is the hybrid network topology, C through Helios, and fourth is the direct network topology, example Camp cube. From another perspective, DCN architecture can be divided into two groups, server-centric and switch-centric. In switch-centric scheme, it places the interconnection and routing intelligence on switches, whereas server-centric scheme expects the servers also to forward packets along with the normal operation. DCell is a typical server-centric recursive topology. Each server is connected to every other server in the network using bidirectional link. DCell 0 is the basic unit of DCell topology, which contains n number of servers along with a mini switch, which is just to connect other servers in the same DCell 0. Higher level D cells are recursively built using lower level cells, making it highly scalable architecture, however still prone to latency issues. Another example is BQ. This is a recursively constructed topology. BQ accelerates 1 to n traffic patterns and also demonstrates a good network capacity for all-to-all network traffic. However, BQ is deficient in scalability and also has high wiring complexity. Another typical hybrid network topology are see-through and Helios. They are the combination of two or more network topologies as shown in the figure. In this section, we'll discuss about DCN operations. Traffic control in DCN is based on the various aspects such as path selection, rate limiting, server latency, and resource sharing. In terms of path selection, there are various protocols which decides on the path in which the packets are forwarded. A typical intra-data center can be built with just switches operating on layer 2 address routing. However, there may be loops due to broadcast packets which can be resolved by spanning tree protocol. Since layer 2 devices don't decrease TTLs, VLAN can be created to isolate network in layer 2 devices. Different VLANs use same subnet addresses but they are basically isolated. Spain protocol uses tree topology and creates different networks based on VLANs. In layer 3, the IP header is involved and layer 3 devices install multiple tables such as neighbor tables, consolidate tables. Out of this, the L3 device will decide which routes to prefer and install those routes in the routing table. Example protocol includes DFR, BSR. In terms of rate control, it can be implemented on the servers in the data centers directly using the protocols provided by operating system. Example IP tables for Linux operating system, NDIS for Windows, and implicit TCP congestion control. A lot of research is already being made to tackle TCP incast, which is a common problem in data center in many to one traffic applications such as MapReduce and search. Deadline agnostic protocols such as ICTCP, DCTCP, etc. have been developed and more emphasis is laid on the congestion control rather than flow completion time, that is latency. For example, the TCP congestion control protocols rely on acknowledgement, and if the acknowledgement is not received, it thinks it's a packet loss and consider it as a network congestion. Explicit congestion notification (ECN) is used to detect the congestion, but it is not so efficient. DCTCP protocol uses ECN to detect congestion. It improves ECN processing by analyzing the bytes received in the TCP segment with ECN bit and the data. This shows the congestion and it increases the TCP congestion window and receive window size based on the obtained results. This is the best method to achieve burst tolerance, low latency, and better throughput with shallow switches. For server latency, we have deadline aware protocols. It can be made use as it not only aim in congestion control but also checks the flow completion time to have minimum latency. Protocols include D2, PDQ, etc. The network security in data center includes security tools to enforce security policies which would prevent threats and vulnerabilities. The security tools or device include stateful packet inspection, filtering mechanism, security controls such as access control list, and detection based on predefined signatures or customer signatures used in intrusion detection systems or intrusion prevention system for both network level devices and host level devices. The figure shows multi-core model which ensures multiple layers of security by dividing network into two layers, the enterprise core, and the corporate core. The corporate core protects the enterprise core by implementing various security services such as SSL, IPsec, VPN, IP or your reputation, web proxies, etc. This is used when users want to connect DC over public IP or an inside user wants to access something from the internet. Enterprise Core ensures network security by having dedicated perimeter firewall L3, L4, L7 firewalls along with the routing mechanism in addition to security zoning. The devices must also be isolated using zoning, example trusted DMZ zones, such as that devices on these zones which don't need any external or internal communication must not allow access to them. Example, a web server or mail servers are kept in DMZ zones as they are allowed to access from internet. But if any of these servers are compromised, the attackers shouldn't gain the access to the trusted zone. Thank you.
In this section, we will quickly have a look at the features a state-of-the-art data center network should have. And the features are simply it should be fault tolerant, it should provide low latency to applications, it should have the right network capacity to support huge data traffic, and lastly, it should support virtualization. Now, what's fault tolerance? Fault tolerance is the ability of a data center network to continue to forward traffic in the event that there is a component failure. So what this means is if your router fails, if your switch fails, or there's a link outage, your data center network should have been built and designed in such a way that it can continue to forward traffic. That is when you can say you have a state-of-the-art data center network infrastructure. And one way of building such a fault-tolerant data center network is to ensure that you have redundant devices. So you have two routers for each segment. If it's your spine, you have two switches. If it's your leaf, you have two switches. You also need to ensure you have physical redundant connection between devices. And lastly, you need to implement a routing algorithm that is capable to quickly detect a failure and recover from it. All this sums up what we call fault tolerance. Now we move on to latency. And latency is simply how long it takes a packet to travel from the source to the destination and back to the source. Network latency is a sum of multiple delays along the path in a network. So it sums up queuing delay, it sums up the transmission delay, it sums up the propagation delay, it sums up the buffer delay. So all these delays summed up gives you the end-to-end latency you have within a data center. And obviously, you want your data center network to deliver low latency to your applications because they require that to function optimally. Hence, it is important that when you are designing or building, you need to have a network diameter that is small. And what that means is the number of hops within your data center network shouldn't be many. If it is, you're going to have additional delay, which automatically increases your latency within the data center. For instance, the table 1 in this diagram or in this image shows the requirement for low latency application. Virtual reality requires about 1 millisecond. Telesurgery requires 1 to 10 milliseconds. But this gives you an idea of the latency that applications need. Now we move on to network capacity. It's also an important feature of any data center network, the ability to have been designed and built in such a way that it can support huge volume of data traffic. And this has to be thought about in your planning stage too. Which kind of network devices are you procuring? Are you procuring network devices that have high throughput capabilities? If you are thinking of if you are thinking of pushing about 100 gig of data, it means if you are procuring these devices, you need to buy devices that have optical transmission interfaces because it's only optical fiber that can support at the moment up to 100 gig of data transfer. Your electrical interfaces can support 10 gig as we can also see in the diagram. The last thing that we need to consider here is virtualization. Any state-of-the-art data center network should support virtualization. It makes life easy for even the server administrator. They can easily migrate their servers from one segment to another segment without them thinking of having to change the IP addresses. And this is where software defined networking comes in. Software defined networking allows you to do network abstraction, and this allows you to be able to provide this kind of services that allow ease of movement on virtual machines. And to conclude, we'll conclude by saying this: if you are this for you to design or implement a state-of-the-art data center network, it's important that you think about security. You implement the right topology, which was discussed earlier on. It should be fault tolerant, it should provide low latency to your application, it should definitely support virtualization, and should have the network capacity large enough to handle huge amount of data. Thank you. And these are our references.